So you don't want to do an expanded octet.
This is Lewis structures?
Yeah.
You can erase the top.
Let's do PCL3, I guess. Okay, so in Lewis structure.
How do we name that class?
One phosphorus.
Chloride.
Thank you, Ms. Weimer. Alright, so when we do Lewis structure, the first thing we have to do is tally up all the potential electrons that'll be involved in bonding. So that's all the valence. So we have one phosphorus, and it has 5 valence. That comes from your column number. And then you have 3 chlorines. Right, I feel like I'm on TV.
Doing great.
7 chlorines. So stiff. Alright, so we have 26 total valence electrons available for bonding. So that's step 1. Step 2 is to divide those by 2 and get the pairs of electrons that we're going to have. Now, pairs come in 2 types. You can have bonding pairs and you can have non-bonding pairs. The non-bonding pairs are typically those that are going to be in your orbitals, your up and down arrows that aren't exchanged. Okay, so we have our pairs. Next, we want to pick the central atom. Now, the central atom is easy to pick out. It's usually, almost always, the one you have the least of. The technical way to find it is the least electronegative in the formula.
That was the most.
No, it's the least. Yes.
Oh, yeah, okay.
So we just then put the terminal atoms. So we have central and terminal atoms. Terminal means on the outside or ending. And I assigned 3 sticks here, which of course now we're going to fix because they don't want us to use sticks.
They don't want sticks.
I'm going to use sticks for now. And I'll fix it in class. So
Sticks is the way to go.
So I have 3 bonding pairs, and I'll have 10 non-bonding.
As a matter of fact, it might confuse.
Now, when we put the non-bonding pairs, you always fill up the terminal atoms first because they are more electronegative. They'll get the electrons. So 3, 6, and 9. So I have 1 remaining pair. Remaining pairs will always go in the central atom. So that central atom will have 1 pair of non-bonding electrons. And the last thing you do is make sure everything has at least an octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8.
Okay, so that's where they could all do this. They knew that that was an unshared, because what we were looking for was unshared electrons, or the ones at the top. And then we put a bubble over it, and then they compare it to what was on the chart. That's as far as they understood. I don't know that they understood what they were doing. Yeah, I don't know that they understood what they were doing. They could do it, but I don't know that they had a purpose for it.
Okay. And finding the geometries last year. They were just following the formula, not really understanding why.
And they really weren't doing all that. They were just doing it.
Okay.
Like, they didn't do all. And the reason is because, if I'm correct, that does not work on the last 2 as well. That confused me. The whole 26 electrons divided by 2, 13. I mean, it worked perfectly for this one, but.
Well, the other one is what you're talking about when we got into the trigonal, binomial, and octahedral.
And those don't follow the rule?
They don't follow
Okay.
the rule. That's why.
Yeah.
Yeah. So most elements that are central atoms are going to follow the octet rule. What happens is that some of the big elements, actually this is one that could do it. So let's say I did PCl5, just for fun here. So that means that I would have 1 times 5, 5 times 7, that's 40, right? So 40, 20 pairs, so 1, I mean all this just to talk. Okay, so that's 15. So in this one, you have an expanded octet around the P. You can have more.
All right, yeah.
Okay.
No, they got that too.
Okay, so
I just don't think they,
understand why they can do that?
no, they got all that.
Okay.
But the reason why are we doing this was unclear.
Oh, why are we drawing structures?
Why are we doing it at all?
Okay.
There was no connection between, yeah, I can do that, but that didn't tell me. I mean, it literally didn't tell them anything.
Right, it doesn't tell you a lot.
Okay.
It really doesn't. The information that we get from structures like this are how many of these pairs, we call them domains, do we have around the central atom? The chain is, we go from domains to the base geometry. So if I have 1, 2, 3, 4, 5, that puts me in that category of trigonal pyramidal,
Right,
or in this case it's tetrahedral.
right, they got that part.
Okay, so then I go from base geometry, the number of lone pairs tells me which specific molecular geometry to go
Okay.
through. Once I've got all that, now I can pick whether it's symmetrical or not, whether it's polar or non-polar.
Okay, got it.
So there's a chain of why we do this. Alone, this makes no purpose at all.
So, but once we decide polar or non-polar, that's when we talk about intermolecular forces and whether it's solid, liquid, gas at room temperature and that kind of thing.
Okay.
That's why I like that's why I kinda like teaching this later
Later.
In
than
the year.
after solutions, after
Oh, okay.
all
Right.
that.
Got it. So when I, in the CAT last year, I never went beyond, this is how you find,
Right.
this is how you fill in these 4 blocks.
Right.
Done, boom.
Cause
Okay.
I think the